So, good afternoon, everybody. So today it's my pleasure to introduce Daniel Kious from the University of Bath, and he's going to talk about random walks on the exclusion processes. Daniel, the floor is yours.
Yeah, thank you. So first, thank you very much for inviting me to talk. I wish I was in Brazil, but this is better than nothing, right? So thank you. And yes, so I'm going to talk about a work that we have done with Marcelo, Hilário, and Augusto Teixeira. So it's a very Brazilian paper. Most of the work was done while I was visiting IMPA, I guess 2 years ago or something close to that. And it's about the random walks on the exclusion process, or more generally random walks in dynamic random environment, right? So just to give you a sort of hand wavy introduction, if you want to think about the usual random walk in random environment, on Z. Okay, everything I'm going to talk about today is on Z. So you can think of it as a random walk on a random potential, right? And what it means that you're going to take a landscape function, right? That looks something like that. Okay, and on this function, you're going to drop a particle, this big blue ball. And this particle is going to roughly follow the slope of this potential, okay, but with some randomness, some chaos, okay, so the ball is moving around, but roughly following the slope, right? So if your function is decreasing, probably it means that your random walk will be transient to the right, right? So here, what we are going to do for random walks in dynamic random environments, so random walks in dynamic random environment, okay, we're going to allow the potential to fluctuate, allow the potential to fluctuate with time. All right. So both your potential will wiggle around, right? And the particle will keep on moving on this potential that is wiggling around. Okay. So the idea is to model the motion of a particle in a viscous fluid, right? Where the fluid is moving as time goes. All right. And the questions you can ask about this model. So I'm going to define the model precisely in a second, right? But just to set the picture. So the kind of question we want to address is, do you have a law of large numbers for the position of the particle at large times, right? Law of large numbers. Do you have, what are the fluctuations of the particle or the deviations, right? So do you have a CLT? Is it diffusive? Is it super diffusive, sub-diffusive? You can ask all kinds of questions, right, about the deviation. Then you can ask further question about ballisticity, sub-ballisticity, trapping phenomenon, and there are questions about atypical fluctuations as well that I will mention later. All right, so that's the overall picture of the problem, right? So in our paper, we deal with two kind of random environments, the exclusion process, something that we call random walks and random walks. Today, I will just focus on the exclusion process because it's you can think of it as the canonical model that you want to have in mind when you talk about random walks in dynamic random environment. All right. So I'm going to only talk about random walking on the exclusion process from now on. Right. But you can think of this model as a more general model. All right. Okay. So let me go on with the definition of the model, right? So, definition. So again, everything is on Z, on Z. So I'm going to start with the environment. Right, so the environment here is going to be the exclusion process. So the exclusion process is going to play the role of this fluctuating potential, right? So the exclusion process, it's a Markov process, eta t, right? Such that for each t, eta t is a configuration of 0 and 1s on z, right? So eta t of small z is either 0 or 1. Okay, so you can think of it as slots on z, right? And each slot has 0 particles or 1 particle. I will make it clear in a second. All right, and this Markov process is defined in the following manner, right? So I'm going to start it with some configuration eta 0 that I'm going to choose distributed like a product of Bernoullis with parameter rho. All right. So what it means that to each integer of z, I'm going to assign 0 or 1, putting 1 with probability rho. Okay, and this rho here is a number between 0 and 1, and that will be the density of the exclusion. Right, I guess most of you know the exclusion process, but I'm going to recall it anyway. So I'm going to put in a frame like that all my parameters, because there will be a few of them. All right, but rho is actually the main one for my talk today. Okay, okay, so you throw your balls, you put a ball on an integer with probability rho and no ball with probability 1 minus rho. All right, and then you need to define the dynamic of this Markov process eta t. I mean, I think the simplest way is to give you the infinitesimal generator, right? So infinitesimal generator will be the following. So you sum over all x and y and z that are neighbors, right? So at distance 1. You look at the pairs such that there is a particle at 1, no particle at 0. Okay, I will draw a picture in a second if you have never seen what's the exclusion process. And then at rate gamma over 2, you're going to ask the particle that is on x to go on y. All right, and you can write it f eta xy minus f of eta. So you go from the configuration eta to the configuration eta x, where eta xy, where eta xy of z is equal to eta of y if z is equal to x. Okay, so x becomes 0. Eta of x if z is y. Okay, y becomes 1, and it's equal to, sorry, and it's equal to eta of z. So otherwise, so if z is not x and not y, you don't change the configuration at z. All right, and gamma is another parameter. Okay, it's the rate of the exclusion process. All right. All right. So yeah, let me draw. So that defines the configuration eta t at all times, actually, right? So if you want a quick picture, if you have never seen what's the exclusion process, so you have Z, this is my slots. Some of the slots have particles and some have no particles, right? So the black slots have a particle on it, right? All right, and each particle is going to have a rate, clock, an exponential clock with parameter gamma, right? And when this clock rings, this particle is going to take a step of simple random walk, so probability 1/2 to the left, 1/2 to the right. Okay, so it jumps to the right probability gamma over 2 and jumps to the left with a rate, gamma over 2. All right, and the exclusion rule is that if this particle here tries to jump on the right, there is no problem. If it tries to jump on the left, there is already a particle on the left, and this jump is just cancelled. It's not allowed. All right, so that's the exclusion rule. You have at most one particle per side. All right, so it's particles that are doing simple random walks, but they are kind of bumping into each other. Right. Okay, so that's the definition of the environment, and only thing I'm going to add here in a corner is that I'm going to write P, bold P. I can do bold. Let's take advantage of the iPad. Bold P of rho, okay, because rho is the density. That's the low, it's low. Okay, and E rho, the corresponding expectation. All right. Okay, so that defines the environment, right? So now I need to define what's doing the particle that I'm going to put on the top of this environment, right? So second. Oh yeah, just a remark that I didn't do. Why I'm choosing eta 0 distributed as product of bandwidth is because that's the invariant measure for this process, right? So you can think as this, you can think of this environment as started from a very long time ago, right? It's at equilibrium. Okay, so it's just going in the background, and that's already at equilibrium. All right. Okay, so now second part of the definition is the walk. Okay, so the walk that I'm going to put on the top of the environment. All right, so what I'm going to do now is that I'm going to fix a realization of eta t. Okay, so the whole history of the process, of the exclusion process. Okay, so I fixed the whole history of my exclusion process. So now my environment is fixed. Okay, it's not really random anymore. The realization is fixed. Okay, and given this fixed environment, I can define a Markov chain. Markov chain xn. So the walk, I'm going to make it discrete time. Okay, so the exclusion is continuous time. Okay, I don't know if there is a clever way to do exclusion in discrete time. I know that Augusto would hate it. But the walk here, which is discrete time, you could take a random walk in continuous time with rate 1, shouldn't change much, but here for technical reasons that are not very deep, we chose to make it discrete time. All right, but everything should work the same for continuous time with rate 1. All right, so given the environment, xn is a Markov chain such that x0 is started, x is started at 0, x0 is 0, and all right, so the probability to jump on the right, so it's the nearest neighbor random walk. Okay, so I'm going to look at the probability to jump on the right or on the left. Let's put the plus in color, +1. Given Fn, where Fn is the natural filtration generated by Xn, right? That's equal to, all right, so what I'm going to write depends on the state of the environment at time n and at position Xn, right? So I'm going again to draw a picture in a second of what it means, okay? So you jump to the right with probability, what we call P full. There is a particle below you at time n, right? So if eta n of xn is equal to 1, right? And you jump to the right probability P empty if there is no particle below you at time n, where you stand, right? And similar thing for jumps to the left, right? So you jump to the left, probability 1 minus P full here, and 1 minus P empty here. All right. So let me just define the measures, and then I will draw a picture for you. Oh yeah, let me maybe just precise something about these parameters P empty and P full. So we choose this P empty and P full like that. So we want them to be non-degenerate, so not 0 and not 1. And here I'm going to choose them like that. So P empty is smaller than P full. Okay, so the fact that they are not equal to 0, not equal to 1 is just that we don't want anything degenerate. So I think the degenerate case would be a bit particular. So we don't deal with that. Okay, we fix them positive and smaller than 1. And this one is actually you can do that without loss of generality, right? Because either PMT is smaller than P full, so this thing, or 1 minus PMT is smaller than 1 minus P full. And then the only thing you have to do is to take Z, flip it around, and you obtain the same thing as what I wrote here, right? PMT smaller than P full in this flipped Z, all right? So you can assume that without loss of generality. So the result I'm going to state holds even without that. Only one word in the theorem relies on the fact that I have PMT smaller than P full. The word will be non-decreasing, but it would just change to a non-increasing if you flip the inequality. All right. So now the measures. So let's denote P eta, the quenched law. So the quenched law of the walk, it means for fixed eta t. Okay, so just what I have defined here. So that's a Markov chain, right? So P eta is the law of a Markov chain. And what I'm going to call this double bar P of rho is its anil law. So the anil law is the law of Xn, but average over all possible environment when these environments are drawn under the law of the exclusion process, right? So you take the average over all possible environment. Under the anil law, Xn is not a Markov chain anymore, right? So if you fix the environment, you have a Markov chain, but if you look at the anil law, that's not a Markov chain, and that's one of the main difficulties. One of the difficulties of this kind of models, right? Both this model and random walks in random environment in general. So if you want, this P rho is actually equal to taking the average over the environments. So that's the measure of the exclusion of the law of the Markov chain. Okay, something like that. All right. I should write like a semi-direct product or something, but it gives you the right idea. All right. So, and if you want a picture, okay, so here I'm taking a snapshot of the environment at time n. All right, there are some places where you have particles and some places where you don't have particles. All right, if you stand here on a site with a particle at time n, okay, so here I am at time n. You jump to the right, probability P full, to the left, probability 1 minus P full. Whereas if you are standing here, you jump to the left, probability PMT, and to the right with probability 1 minus PMT. All right. Okay, and that defines everything about this model. All right, so I'm just going to drink while it sinks in. So what I'm going to do before studying the results. So what the result I'm going to state is going to be a law of large numbers and CLT in some regimes. I just want to talk about the literature first. So there is a lot of literature about random walks in dynamic random environment in general. So, but most of the papers up to our paper were dealing with perturbative regimes, meaning that there was one of the parameters or some of the parameters that you would need to take to extreme values, right? So either a very large density or very small densities or very large bias to the right or something of that sort, right? And yeah, most of the paper was dealing with this perturbative regimes. But the big advantage for us is that they were there and they actually developed a lot of the techniques that we used in our paper. And actually, Marcelo and Augusto were among the people that developed all these techniques. So just to cite a few papers, there was a paper of Avena, then Hollander and Redding in 2009, where they considered general model of random walk in a dynamic environment, but they asked that the environment satisfies something called the cone mixing condition, which is some condition that asks the environment to mix very fast, exponentially fast in front of the particle, right? Which is not the case for the exclusion process, right? Exclusion process mixes fairly slowly, right? And definitely not exponentially fast, right? But I mean, it was a very nice paper that developed a lot of the techniques. There was a later paper of Hollander, Castanet, Vicius, where they consider a similar model called random walks in random walks. So instead of the exclusion process, you consider a Poisson cloud of random walkers, which we do in our paper too, actually. And they proved some weak law of large numbers when the density of the particles of the environment go to infinity, right? So that was a very perturbative results, but a very nice paper. And then after that, there was a very long sequence of papers by a lot of people. So subset of Oriane Blondel, Frank Daniel Hollander, Marcelo Hilário, Renato dos Santos, Vladas Sidorovicius, Augusto Teixeira, and probably many others that I forgot. But one that is important in the framework of this paper is the one by Blondel, so Oriane Blondel, Marcelo, and Augusto. And I guess that's 2018, I guess. Maybe it was on the archive in 2018, I'm not sure. So in this paper, they considered a general model of random walk in dynamic random environment. They asked for a mixing condition, but much weaker than the cone mixing, right? So they just asked some polynomial mixing speed, right? Still asking too much for the exclusion process, but much better than everything that was before. And the big thing that helped us a lot is that they develop a very strong and very nice strategy for the renormalization techniques that I'm going to explain later. Okay, so that was very useful to have their paper, and all the previous papers. And another paper that I'm going to write down is the one of François Wieners and François Simnos. That's 2015. So in this paper, they exactly look at the model that I defined, random walk and exclusion process. But again, they get some perturbative regime. They need to take gamma, so the rate. So they play on the rate of the exclusion process. And they need to take either a very low rate or very large rate. And they prove law of large numbers and CLT under these perturbative regimes. And what was very useful for us is that they define on the way some regeneration structure that I'm going to talk about in my talk. And that was very useful for us to have this at hand, right? And that's actually the main reason why we choose XN to be discrete times, just to apply their regeneration structure. All right, so I didn't write all the papers that I quoted. It means too much of them, but they were useful, all of them. But these two played a particularly important role in our work. All right, so now let me just state our result, right? So here I'm going to fix all the parameters except one, which will be the density. Okay, so the parameters we had the rate gamma, we had the transition probabilities, right? P0 and P4, and that's it. So all parameters except the density gamma. Rho, sorry, not gamma. All right, so I could allow 0 and 1, but these are easy cases, right? If you have absolutely no particle or particles everywhere, that becomes a usual random walk, right? A biased random walk. All right, so theorem 1. So there will be a theorem too. So that's Marcelo Hilário. That's us, right? Myself and Augusto. So the paper was published in 2020. So my first point is going to be a law of large numbers for all densities except two values of the density that I'm going to unfold afterwards, right? I'm going to explain to what are these two densities. I will write a definition, but maybe it will not be super clear, but I will explain it, all right? So there is a deterministic function v from 0, 1 to minus 1, 1, non-decreasing. So that's where I'm using that PMT is smaller than P4. But again, if you have the other inequality, then it just becomes non-increasing. Okay, that's not a big deal. Such that, well, xn over n converges almost surely to V of rho. All right, under the anneal measure. So P rho almost surely. Okay, so P rho means that I've chosen my density to be rho, and that holds for all rho in 0, 1, except two values that I call rho minus and rho plus. So just these two values, okay, and that are defined like that. So let me just, so that's the law of large numbers, right? So rho minus is the, what it is? It's the largest speed, largest density, such that V of rho is negative, and rho plus is the smallest density, such that V of rho is positive. All right. Okay, I'm going to draw a picture of the speed profile in a second to unfold this result. And the second point of the theorem is a central limit theorem in some regimes. So in the regimes that are actually where V of rho is non-zero, right? So moreover, for all rho where V of rho is not zero, so 0, 1 minus the interval rho minus rho plus. So I'm also removing rho minus and rho plus. I don't even know if there is a speed at rho minus and rho plus anyway. So in particular, this implies that V of rho is non-zero, right? Then I have a usual CLT. So if you look at xnt minus nt V of rho, you divide that by rho, by square root n. You see that as a process that converges in distribution to a Brownian motion BT under the annealed measure n, right? And so the annealed law of this process converges to a Brownian motion, and the Brownian motion is just non-degenerate. Okay, I'm not saying that it's a standard Brownian motion, all right? But it's non-degenerate. So that's our theorem, all right? Okay, so let me just explain it a little bit. So I'm going to draw a few pictures that are representing the speed as a function of the density rho. All right, so that's V of rho. That's rho. Okay, so what I'm saying here is that okay, so the general picture, I cannot draw it, right? Because it depends on all the parameters. It depends on PMT, on P full, on gamma, and so I'm going to, in some sense, draw the most general picture, right? But it could be that the speed is always positive, right? If PMT and P full are both strictly larger than a half, then your speed is always positive, right? Because you're not dominated. You dominate a biased random walk with parameter PMT, right? So here I'm just drawing a general picture, right? So you can have a negative speed. Okay, so values of the density where the speed is negative is, okay, let me write it. What you want to think of is PMT smaller than a half and P full larger than half. All right, and the canonical case you want to think about is maybe P full equals 1 minus PMT. Okay, so the two drifts are opposite to each other. But the statement is true in more generality, right? Okay, so you could have negative speed, then you may have a jump from a negative speed to a zero speed here. Then you may have a flat piece where the speed is zero for an open interval of densities. And then you may have a jump from a zero speed to a positive speed. All right. And V of V should be monotone, right? Okay. So, and in my picture, these 2 points where you have jumps are actually rho minus and rho plus. All right. So maybe the picture, the actual picture, if you fix, you choose some parameters, PMT, P gamma, and so on. Maybe the actual profile of the speed is something much nicer, right? Maybe it's that, right? Or maybe it's not, still with a flat piece, maybe, right? And this rho minus and rho plus are still here, all right? But actually, in this case, if there is no jump, we know that the speed at rho minus and rho plus exists and is equal to 0, right? So I didn't write it in the statement to stay light, but that's something we can do, that we do in the paper. Or most likely, the profile is just like that, right? Okay, and you have just one density here, rho minus equals rho plus, where you have 0 speed. Okay, and if the picture is that, then we can say that the speed exists and is 0 at rho minus equals rho plus, right? And this remark is related to the theorem 2 that I'm going to state now, which is, oh, let me tell you something more before. I talked about the law of large numbers, and what we say about the CLT is that the CLT exists in the phases where you have non-zero speed, right? So here, yes.
Do you expect any more regularity of this graph? I mean, more than continuity, for instance?
Actually, we don't even prove continuity.
Even in the perturbative regime, you don't know if is there analytic.
I mean, we kind of know it. I mean, we convinced ourselves that we knew how to prove that it was continuous, but it was a bit of a hassle to do it in the paper. It was adding too much. We had to redefine the regeneration structure and so on. But I mean, it looks pretty clear that it's continuous in the non-zero speed regimes, right? Mm-hmm. So if you're outside, away from rho minus and rho plus, but more information than that, well, maybe you can get, yeah, a bit more than continuous, but I'm not sure what you can get.
Okay, thanks.
Welcome. Yeah, and I saw there was a bunch of questions that I didn't see in the chat about, yeah, everything is annual measure, right, in the statements. All right. Okay, and there are actually open questions about what's going on in terms of fluctuations when you have 0 speeds, right? So there are conjectures in the physics literature that conjecture that you may have some atypical fluctuations, in the sense that the random walk may be super diffusive when the speed is 0, but it's really, and actually there are conjectures about the exponent, right? So the question is, if xn over n goes to 0, then can you find some alpha such that this converges, right? This converges something non-trivial. right? And the conjecture that this alpha is not a half, is larger than a half, and there are conjectures about the value of alpha, and they don't all agree, right? So I mean, I in the physics paper I've seen both usual suspects, right? 2/3 and 3/4, and I honestly have no idea which one is the right one, and if it's not a half, right? I know, for example, that François Evners is convinced that everything is diffusive, but I don't know myself. It's a big mystery to me. All right. Theorem 2, it's not about the fluctuations when you have zero speeds, but it's just one byproduct of our theorem, actually, which states the following. So in the particular case where you choose PMT to be equal to 1 minus P4, all right, and you choose rho to be exactly equal to a half, so you're in a fully balanced environment. So it's still random, right? But it's balanced in some sense, as many holes as particles, and the two drifts are opposite to each other. Then it's very natural. Xn over n goes to 0, p 1/2 or more surely, where this p is the annealed measure. Right? So it's a very natural theorem, but that was an open question up to now. And even though it may look like a simple consequence of symmetry, it's not, right? It's more a consequence of symmetry and theorem 1. So, but the fluctuations for this regime, for example, are still not understood, right? So if I had to give you 2 remaining questions, well, there is one on which actually we are working with Marcelo Augusto, Rangel Baldasso, and Enrique Chavez. So the first one is rho minus equal to rho plus, right? So can you say that this flat piece with zero speed cannot exist? Okay, so I think we tend to prove that they are actually equal, at least in some sense, in some cases. But I'm actually a bit sad, right? Because the way I was saying this flat piece was, if you had the flat piece, it would mean that you have a regime where the random walk is transient but with zero speed, which happens for usual random walk in random environment because you have traps in your environment. But it's not clear if it happens for this model, right? So some people say, no, you cannot have traps because the environment moves too much, so they kind of vanish too much, too rapidly, so you can't really sustain them. But you can find arguments that tell you, oh no, maybe there is some effects that sustain it, right? So it was not clear, and I must admit I was very keen on having a transient zero speed regime, but I think from today it looks like it doesn't exist, but we don't have a paper yet. And yeah, the big one is the fluctuations when V of rho is equal to 0. Okay, then you can talk about higher dimension, everything, natural extensions of the theorem, but I think that's the 2 main interesting ones to me at least. All right. So how long do I have, Marcelo? Like 10 minutes, 15 minutes? You're muted. I see you.
Sorry.
I don't see any lips.
Yeah, you have like 10 minutes. You can make it 15. Yeah, 15 minutes.
All right. All right. So I think even 10 minutes,
Anyway,
I can give you an idea.
We are not very stressed, but yeah, like 15 minutes is fine.
All right. So idea of the proof. I'm not going to give you the whole proof because we'll be there until tomorrow. But I think in 10 or 15 minutes, I can give you a good idea of how it works. So the first step I'm going to do is the following. So I'm just going to explain to you how you prove the first part of theorem 1, right? So Xn over n converges to a V of rho if you're not exactly on rho minus and rho plus, right? So the problem to start with that we don't know what's V of rho, right? We want to prove that Xn converges to some speed, but we have no idea what is this speed. So the first question is having good candidates for the. All right, and there are two good candidates that you can think of, and actually that were used in other papers before us. That's what we call the upper speed and lower speed. So the upper speed V plus of rho. Okay, I'm going to write a loose definition, right? It's not the definition that you're going to find in the paper, but that gives you the right idea. So V plus is the smaller speed, so infimum of V, such that the lim inf of the probability to go faster than V at time n is 0. All right, so again, I'm going to draw a small picture to explain this definition a little bit. And V minus, so it means that if you look at the speed larger than V plus, well, the lim inf of going faster than that is 0. Okay, and V minus is the sup, so the larger speed, such that the lim inf of going slower than V at time n is 0. All right, so if you want to draw like a diagram or whatever the name is, a picture. So here it's Z, here it's T, and you can think of this is where the random walk is going to live, right? So what I'm saying is that there exists this V plus here, and there exists this V minus here. And by definition, there exists a subsequence of times where you're not very likely to be on the right of V plus. Okay, not very likely, meaning the probability goes to 0 along that subsequence. Okay, I don't know at which speed, and I don't know if it's a proper limit, right? And same thing on the left, right? You're not very likely to go slower, and actually we don't know if these times on the left or on the right are the same, right? They are not the same in general. You don't know anything, okay? Yeah, and actually to start with, we don't even know if V minus is smaller than V plus, actually. That's something we had to prove in a quite a complicated way in the paper, right? So that's the definition of V plus and V minus. The good thing is that V plus and minus of rho always exist. Okay, you can just define them like that. Okay, so we have something to work with. That's good. But the drawback is that they give only an info along a subsequence of times, right? And this info is not quantitative. All right, so the goal now is to actually make this lim inf, to turn this lim inf into a limit and to have something quantitative, okay, to have a speed of how fast this limit goes to 0. All right, so I'm going to give you a two-step proof of the main statement, okay, and actually this two-step proof doesn't work, but it would have been better if it would have worked. Okay, so let's say two strategy of the proof. Okay, well, first strategy, the one that you should think of, is the following. So you could first, in order to prove the law of large numbers, you can prove that the probability, I mean, we can't prove it, but that would be a nice strategy, okay? To go faster than V plus decays fast. Okay, and respectively slower than V minus, decays fast as well. So I'm leaving a space here on purpose, right? I'm going to change what we actually prove. So fast enough or fast enough, I mean anything that would allow you to use Borel quantity lemma essentially, right? So stress exponential, we don't even have stress exponential actually, but we have something larger than any polynomial, so that's good enough. All right, and the second step, you could try to prove V plus equals V minus, right? And you would be good, right? Because the first item would tell you, okay, if you look at your picture here with V plus and V minus, well, you have a limit in the strong sense, right? So actually, for large time, you will be forbidden to be in this red zone, right? So your random walk is going to live in this cone. And the second step tells you, well, actually, this cone is flat because V minus is equal to V plus, right? So if the cone is flat, so here it's V equals V plus equals V minus of rho, everything, right? It means that I am forbidden on the left of it, forbidden on the right of it. So the only thing I can do is follow this straight line here. All right, and that gives you the law of large numbers. Xn over n converges to V. All right, and unfortunately, we cannot use this strategy, okay, because of correlations in the model that I'm going to explain in 2 minutes. And what we prove is that you cannot go faster than V plus maximum 0, and you cannot go slower than V minus minimum 0, right? So that's not what we prove here. The picture that we have is, so 1 plus 2, the real one. It tells you that, okay, you know that we still have 2, okay, that V minus equals V plus, so that's V. We cannot go, so here I'm assuming that V is positive, okay? So if V is 0, actually, it's already a proof if you have that. But let's assume that V is positive, then, okay, I cannot go faster than V maximum 0, which is V here. And I cannot go slower than V minimum 0. So here, just I cannot go slower than 0. Okay, that's all I can say. So unfortunately, in that case, we still have an open cone that we can travel within, right? So to finish the proof, we had a third point, okay, which tells you that, okay, if, let's say, V plus of rho equals V minus of rho equals V of rho is positive, then there exists some epsilon positive such that the probability to go slower than epsilon at time n decays fast. All right, so what I'm doing here is that I'm tilting here the y-axis here, and I say, okay, you cannot go slower than epsilon actually. So here it's 3, right? So it doesn't look like much, but actually it allows us to use the so-called regeneration structure of Seminário and Wiener and Seminário. And regeneration structure, it means, so if you go faster than epsilon, okay, you know that you travel at a speed that is much faster than what the exclusion process, than the speed at which the exclusion process is evolving, right? Exclusion process, it behaves like a diffusive thing, right? Because all the particles are moving like simple random walks, bumping into each other, but still. Whereas you move very fast, so it means that somehow your environment, the environment that you will see around you, will refresh quite often. Okay, and if the environment around you refreshes quite often, there is a way to say, okay, actually I can cut my trajectory into IID pieces. That's the regeneration structure, that's the regeneration strategy. And once you have these IID pieces to describe your trajectory, you can apply usual law of large numbers and CLT. All right, so that's the global strategy. And in 4 minutes, I can explain to you how you you see the V plus and V plus maximum 0 and V minus minimum 0, right? And that's because of the techniques which are here based on renormalization. Okay, so the idea of renormalization is to study events of the form xn goes faster than some speed v. Okay, so xn is larger than n times v. All right, and control its probability or their probability at larger and larger scale. So if you have already seen talks about renormalization, often people say that the goal is to turn a qualitative statement into a quantitative statement. So that's exactly what we want to do with V plus and V minus. All right, and what we do here is the following. So we take a big box, okay, that we are going to, I'm going to tell you the size here is HLK plus 1. So LK plus 1, I'm going to define it. Here it's HLK plus 1, and this big box is paved with smaller boxes of size HLK. Okay, and here my sequence HLK is defined recursively for all k by something like LK to the 5/4. Okay, doesn't matter the precise stuff. We could have chosen something different, but turns out that's what we have chosen. Okay, and the event I look at is going faster than the speed v. Okay, so my random walk. Oh, sorry. So I should say, what is this picture? It's a space-time picture again, right? So that's time, that's z, right? And what we are saying essentially in the renormalization procedure is to say, okay, if the bad event xn larger than nv happens at scale lk plus 1, right, I can find two boxes where two boxes of size HLK where this bad event happened as well, right? So, and if this happens, you can write the following recursion inequality. You can say that so let's say that this event is AK plus 1, and these ones are AK1 and AK2, the bad events, right? So you can look at probability that AK plus 1 happens, and you can say it's smaller than some entropy term, which is the number of pairs of boxes, okay, which you control very well, times probability of AK squared, because these two boxes are bad boxes, okay, so AK happened in there twice, probability of AK squared, but here I'm pretending that these boxes are independent, which they are not. So I'm doing some error that I need to factor in, all right? And okay, the entropy here is actually smaller than LK. So you have LK times probability of AK squared plus some error. Okay, and the idea is to say, okay, if I can control, if I know something about probability of AK, okay, so if probability of AK is smaller than, let's say, exponential minus log 3/2 AK, and the error is much smaller than that, okay, then it's a straightforward computation to see that probability of AK plus 1 with the recursion I've written above is smaller than exponential minus log 3/2 of LK plus 1. Okay, so bottom line, if I know an estimate at scale K, and if I can control the error, then I can carry on the same estimate at scale LK plus 1. All right, so now why can we deal only with V plus maximum 0 and V plus minimum 0? That's because, well, we need two things to make it work. We need to trigger the renormalization. So we need the first estimate, right? That probability of AK0 is satisfied, is smaller than this threshold for some K0. Okay, so I'm not going to talk about that. That's actually the role of this small h here, but let's put it on the side. And the big stuff is that we need to control the error. Okay, and to control the error, that's the last picture I'm going to draw. You have to realize that for the exclusion process, if the two boxes that you, so let's say that V is negative, right? Let's say V is, come on. V is negative, and look at the event to go faster than V here. then the two boxes, maybe the two boxes that you find where the bad event happens, the small boxes are on the top of each other. And for exclusion, it's bad because if you look at the correlation for the exclusion process, well, they behave like that. If you have a box F1 and F2 that are at distance t, well, the covariance of F1 and F2 is at least 1 over square root t. You can think about a random walk starting here and ending up at the same position in the upper box, right? So the correlation is at least 1 over square root t. And 1 over square root t is much larger than this threshold exponential minus log, blah, 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 right? So it's not good enough. So the thing that we say is that if you're not in this situation, right, if the boxes are well separated in space and time, okay, so if they're along a positive slope like that, okay, they will be separated. For example, if here it's h, the distance here will be at least, so it will be proportional to h, but let's say at least h to the 3/4. Okay, then if you are like that, then the covariance is, let's say, just small enough because I'm running out of time. All right, so the covariance is small enough, and that implies that the error term is small enough. Okay, so that's why we consider this V plus maximum 0. And what we just, this fact, that's just a simple fact actually that we proved in the paper, we call that the lateral decoupling. Okay, so if the boxes are well separated in space and time, okay, then you can actually decouple them well. And that's how you get the first point in my strategy. The second point, V plus equals V minus, it's also based on renormalization, but the proof is much more involved, okay, much more complicated. And the third point, actually, it's again similar renormalization, and we need to use some sprinkling technique that was proved by Rangel Baldasso and Augusto Teixeira. And yeah, and that's how we put everything together. So I'm sorry that I have to hurry that much at the end. Usually on a real talk with a real board, I can make it in 50 minutes, but it looks like it's taking more time on an iPad. So we'll stop here. Sorry for being late.
Okay, thank you very much, Daniel. Let us just thank Daniel for a second. All right. Are there questions?
I have a question.
Pablo?
Pablo.
Yeah.
So you have this limit of the speeds, and this does this tell something about the probability that the random walk is over a particle or over an empty site?
About the probability that it is over, yeah, no. Like you want to have some information about the random environment, the environments in from the particle, right? Yeah, no. We actually, no, we can't not say. I mean, the only thing that we say is that the speed exists, right? Then there's, I think there's a paper of Renato dos Santos.
Because the speed will give you the density, right?
If we had the speed, yeah, but we don't have it.
Yeah, of course.
Yeah, the only I think the only result I can think of is a paper of Renato where he proved that the speeds are not on the boundaries, right? If PMT is different than P-full, then the speed cannot be like 2 PMT minus 1 or 2 P-full minus 1. It's somewhere in between strictly. But that's about it.
Okay. Thanks.
Welcome.
So there is one question in the chat by Shanji. How would the result change if considering a SSEP instead of a simple symmetric exclusion process? So the asymmetric.
Yeah, so I think I think we could get something similar. I mean, I don't know if we could get it to be. I think it would be actually a lot of work. First, I thought it would be kind of easy, but after thinking about it a little bit, it's not easy. But maybe you can. Probably you can adapt this lateral decoupling that I talked about for the ASAP. I don't think that would be a huge problem. And maybe you can have a statement that is very similar to theorem 1, right? Except that the place where you would have a problem would not be v of rho equals 0, right? So here the problem is v of rho equals 0. That's where somehow the interactions between the boxes are maximal, right? But for the ASAP, it will be when v is equal to the characteristic of the ASAP, right? So the speed at which the information travels. And there you would have problems because exactly along that speed, the lateral decoupling wouldn't apply. And your boxes, if you have two boxes that are along this slope, then you would be in trouble. But it's not that easy because even, for example, the sprinkling, I don't know if it exists for the ASAP. I don't think so. So that looks like some proper work. But lateral decoupling should be fine. Renormalization should be fine. And the rest of the proof that I did not talk about, well, it's complicated, so I cannot answer really, but probably you can make it work. I think the biggest problem I see is the sprinkling.
Yeah, right. More questions?
So can I ask a question?
Yes, sure.
So with respect to Sanjay's question about the ASAP, that's somehow it's expected that ASAP mixes faster than the exclusion process.
Yeah.
And so instead of mixing at if you look at the box of size n, instead of mixing at times of order n squared, it should mix at times of order n to the 3 over 2. Will that change your proofs somehow make them easier or more difficult? I don't know.
Well, I think the problem is that 3 over 2 is still larger than 1. So I mean, there wouldn't be it wouldn't be an easy fix, right? You would still need some extra argument, something geometric or something, you know. It's not like, oh, it's mixing fast enough, therefore it decouples well and so on, right? Because I mean, yeah, you want your error to be summable, right? And here it wouldn't be summable just like that.
Okay. And another question, it's that I just wanted to know what is your current position about these conjectures of the zero speed case, because in our paper, you know, with Octavio Meneses, where we prove that. So you know that the scale is different because we play with the gamma, no, with your constant gamma. And we argue that the limit should be this fractional Brownian motion in that case, right?
Yeah.
So I just wanted to know what is your current opinion about this?
I don't know. I feel like there will be something fun, like non-diffusive. I still don't get to what would be super diffusive intuitively, but yeah, I mean, there are these arguments of François Huvener's where he says that actually it's the super diffusive effect only lasts just for a while and then vanishes. But it's like physics arguments, right? It's not proper math arguments. But yeah, I only half believe in them, but still they are these arguments, right? So maybe that's what's happening, right? That you have something super diffusive in the first time scale, and that afterwards you become diffusive.
Because
I remember.
Okay,
Augusto.
Sorry.
Yeah, I was just going diffusive, and then he used the same argument that I was using to convince me that it was sub-diffusive. So I failed completely.
I see.
Yeah. It's hard to answer anything, right?
So I was thinking in a different direction. So last time I modified my conjecture a little bit, because there is still one extra parameter which you can play with, which is the probability P naught and P full. Because you can take more complicated functions of your environment.
Yeah.
And I think that depending on the behavior of this local function, you get different behaviors. So I think so nowadays that's my current conjecture, and that what makes things much more complicated, no? Because it's now you have to really worry about the exact details of interaction.
But you think even with a local rule?
Even with a local rule, it makes difference.
All right. Yeah. So it makes it harder to answer your first question.
Yeah. Okay. If that's true, it means that the answer to the question is not just
yes or no. Yeah.
Yeah.
Even if you think about random walk, about the environment seen from the particle, we more or less know that it depends on all the parameters, right? So if you find some nice formula, it will have to depend on gamma, on everything, right? So it doesn't look easy to get one or to think of one. And I think at some point I convinced myself that it was not a product measure, so it's even worse. But yeah.
Okay, thank you.
Yep. More questions? Okay, so if not, let's just thank Daniel once more. Thank you, Daniel.
Thank you.
So the seminar just continues in 1 week with Herbert Spohn next Wednesday at the same time, at 1 o'clock Brazilian time.